That's it. Just the mass chaos.
So thank you all for being here today. It's my pleasure to introduce Miguel Bernardez. Miguel got a master's degree in physics, he did get a master's degree in physics. That was in 2017. His undergrad is also in physics. But his physics master's degree actually made use of some of these ideas, in particular this way of parameterizing large-scale dynamics to look at tropical cyclogenesis processes. In his free time, Miguel likes to play disc golf and soccer. And he just recently took part in the OTREC field campaign, where we went down to Costa Rica for 2 months and used an airplane to take measurements of vertical motion profiles. And he'll tell you about the bottom-heavy vertical motion profiles we observed at the end of his talk. So this work is related to OTREC, but we haven't yet made use of OTREC data for doing it. So,
Thank you. Yeah, welcome everyone. Today, like Larissa said, I'm going to be talking about my investigation of bottom-heavy vertical motion using parameterized large-scale convection, or large-scale dynamics. General outline of the talk. First, I'm going to go over some basics of tropical meteorology, and specifically the weak temperature gradient and how it's a useful tool for simulating convection. Then I'm going to talk about bottom-heavy vertical motion profiles and how they're important to the tropical energy budget. Then I'm going to go over the two potential causes for this, which are simply a thermodynamic cause and a dynamic cause, essentially. And then I will talk about the SWTG simulations that we actually did, and then finally a little bit about OTREC that we were studying. So the basics of tropical meteorology is that the large scale and the convection itself are extremely intertwined. Any convective heating that we have has a large scale effect, and the large scale also has consequences for the convective heating itself. Here are two schematics of MJO, which is an example of this kind of interconnectedness, where a propagating wave of both dynamical and thermodynamic effects can propagate as they're intertwined. And the heating itself is extremely important to what is happening in the tropics and setting up what the large-scale dynamics do. And in particular, the height at which the heating happens is extremely important. The vertical motion profiles help in part determine what the latent heating profiles are. Latent heating profiles are directly related to vertical motion by the vertical gradient of dry static energy. But the profiles of vertical motion also affect everything. They affect the large-scale circulation. They affect how much energy you're importing and exporting. They affect the radiation budget in terms of the higher your cloud tops, the more radiation, or the less latent heating, the less long-wave radiation you'll have to space. And it also, so for instance, in the West Pacific, we have a balance in convection between the short wave and the long wave, which isn't necessarily true for all cases. In particular, this bottom-heavy convection that we're studying has different rates of latent short wave and long wave heating. And these profiles are also important to things like climate sensitivity in models, as well as things like the location of the ITCZ. But these latent heating structures are both difficult to observe and difficult to simulate. Here are a few different examples of the latent heating profiles that we need to get right in order to properly simulate tropical meteorology. But the current observations are extremely limited, which is part of why we have the OTREC field campaign in order to take direct measurements of both the vertical motion and the latent heating profiles. And the OTREC data set is going to be extremely important for testing our hypotheses. on actual data, not just simulations. The thing that makes tropical meteorology both complicated and fairly simple is the fact that around the equator, where the Coriolis force goes to 0, we have the Rossby radius goes to infinity. That means that gravity waves can redistribute temperature anomalies very quickly. A consequence of this is that horizontal temperature gradients are very quickly redistributed. Here is a map of the 600 hectopascal potential temperature. And as you can see in the tropics, we have a horizontal gradient of maybe 1 or 2 degrees across thousands of kilometers, as opposed to the middle and high latitudes where we have much more sharp gradients. The consequence of this is that we can basically ignore horizontal gradients in temperature wherever we see them in the equations, and thus vertical motion is the only, or convection is the only source of vertical motion. Another more old-fashioned way to say this is we don't have a solenoid term in the tropics. So that means in order to properly understand what's happening, you have to know the vertical motion and the lapse rate of temperature, and those two combined give you basically all of convection. And so in order to properly understand what's happening, we need to understand the vertical motion. But one of the benefits of this is that it simplifies our models and the math considerably, because we get to ignore the horizontal temperature gradients. And we make use of this in the weak temperature gradient approximation, which essentially allows us to disentangle the convection from what the large-scale parameterizations are doing. So when we do these models, we have a limited domain cloud resolving model with small domain sizes and pretty good grid scale sizes. And this handles all of the microphysics, the radiation, all of the basics. And then we have on top of that a parameterization for the large scale that allows us to essentially have our column communicate with the environment in a realistic way. This is, so we have one part that handles all the physics, one part that allows us to communicate with the environment, and that gives us a broad or a general model for the tropics, which allows us to study specific mechanisms in simple models which are more cost effective, both time and computation wise, and also more simple so we can more easily understand and we don't have to drag through the data as much. The way the model actually functions, we have, as I was saying, internal components and external components. So here's the budget for potential temperature, and we've separated the winds into an internal component and an external component. And in order to specify the external component, we say that we ignore the horizontal temperature gradients, which gives us only the vertical velocity times the vertical lapse rate. And then we say that this has the effect of moving our domain mean temperature towards our environmental temperature at some relaxation rate, which is what the effects of the large scale have on the tropical environment. They tend to move the environments towards an equilibrium or a quasi-equilibrium because it's at a finite relaxation speed. This is one of the reasons why CAPE isn't very important in the tropics. It's more the consumption of CAPE than actually how much CAPE you have in general, because you can have as much energy as you want, but it's only going to move you towards an equilibrium temperature and not consume all of it. One thing you can do to improve this formulation is to decompose the vertical velocities that you calculate spectrally. And this has the important effect of allowing you to have different gravity waves from different modes move at different speeds. Under the strict SWTG approximation, all modes move at the same velocity, which gives you troubles in terms of response time and how well your simulations actually respond to heating anomalies. If we decompose the heating and project it onto our vertical modes, which we can either just use basic Fourier decomposition, or we can use basis functions that we calculate from the actual stability of the atmosphere. But we project the heating anomalies onto those and then calculate how much vertical velocity for each mode we need. And this gives us a much more realistic wave speed per mode number, which provides several benefits. The first, like I said, was the improved response to heating anomalies. The other benefit is it creates the response to the heating anomalies is more smooth. And another benefit is we don't need special treatment for the boundary layer. Normally, we would, because the boundary layer acts as a constant large source of heat, the WTG doesn't act quickly enough to remove the heating anomalies, and so we have to have a special special treatment there. But under spectral WTG, this requirement is removed. So with the SWTG has been used to study everything from very simple thermodynamic responses to, or the response of convection to thermodynamic changes, all the way to MJO and cyclogenesis, tropical cyclogenesis.
So in your,
yes.
One of your first pictures, you showed that the net heating profile from radiosondes is really kind of different from most models, and most models are different from each other.
Yeah.
So in the lower right, if we accept that as somehow maybe closer to the truth or not, I guess that's the first question.
Yeah.
Is the soundings right, or you don't think so?
Well, there's a lot of uncertainty. Part of the reason this research is important. I think we tend to believe the soundings over the simulations. And
Are differences at all related to this gravity wave issue that you're discussing?
Possibly, but I'm not sure. I believe if you looked into the models, there would be some difference in how those are handled or parameterized by each model, and what the cumulus parameterization actually, or what the parameterizations look like, but that's a little, I think, too complex a question to be directly answered.
The gravity waves lead to an equilibrium that can look like any of these. Right?
Okay.
So,
Cool.
but it's not, I mean, models know how to simulate gravity waves. Right? That's not
Yeah.
the heating that they're responding to, they don't know how to simulate. It's being evened out by the gravity waves.
Yeah, like Bruce was saying, part of the problem is we know the response to heating fairly well, but it's understanding what actually causes the heating, or what the heating itself is doing. But one part of the WTG simulations is it has a phenomenon known as multiple equilibria, where depending on the initial conditions of the model, we can either approach a moist equilibrium or a dry equilibrium. If the model itself is not importing enough energy, which is given by the NGMS, the normalized gross moistability, which is essentially just a measure of energy import and export, we can arrive at a dry equilibrium. This is important for two reasons. The first being the dry equilibrium basically gives us no information, and so we try to avoid it in order to have actually good results that we can analyze. But it is also important because it may have to, it's related to convective to aggregation, in which these moist profiles act and look like the moist centers of models with convective aggregation, while the dry equilibrium look like the dry spots. And
Can you briefly describe what convective aggregation is?
yeah, so convective aggregation is the
Soft aggregation.
yeah, it's the I guess models, once they reach certain size and complexity, tends to aggregate the moisture and convection into small clusters, leaving large swaths to be basically completely dry and driven solely by radiative cooling to space.
And this has horizontally homogeneous boundary conditions.
Yes. So this happens not because of any sort of parameterization in the model, but just because the physics tends to move it this way. One explanation for this is basically this is an energy balance between convection creating heating anomalies and then the wide dry areas removing the heating anomalies. And because convection tends to do it much more quickly and much more powerfully than the radiative cooling of these areas, you need an aspect ratio that is much more tilted towards the dry regions in order to balance those energy buckets.
So is that a model artifact because of boundary conditions? And so how does that translate to a population of cloud elements in the tropics?
Yeah, I think that's somewhat of an open question.
Okay.
In which we aren't sure if this represents an actual physical phenomena, but we know many of the same mechanisms that lead to convective aggregation are present in many different models,
yeah,
and also are present in the real atmosphere. This is I don't think this is a model artifact, mostly because of how many different kinds of models show the same kind of behavior, and the fact that it is tied to actual physical effects and mechanisms. But that is somewhat of an open question, whether it is just simulations showing differences from reality.
It's a whole area of study. People study convective aggregation and the processes that lead to this in models.
Because it seems
There's
to me
thought
that
to be climate dependence potentially.
yeah, there should be some relationship between how much heat has to be lost at the cloud top and how much can be lost in surrounding clear areas, and so that, you know, a mosaic of moist and dry phases of this equilibrium is the optimal way to shed the energy that needs to be shed in these latitude bounds. That's kind of what I'm thinking, but it might be way off track, but that's what I'm kind of thinking.
And I believe when you do something like the Arakawa-Schubert parameterization, which has a bunch of different clouds, each entraining and detraining at different heights, I believe those also show convective aggregation once you get the model big enough and with properly parameterized physics, but I'm not sure specifically on that.
Very
But
interesting.
yeah, this
This is a very idealized geometry, and this happens in a lot of models.
yeah.
But there's no sort of physical reason why the convection couldn't be spread out into a bunch of like randomly spaced gray areas
Okay.
Yeah.
rather than all clumped together like this. And so understanding what controls how
Oh,
much this will happen.
yeah, there
with
isn't
climate
any.
change.
There isn't any.
There isn't any. No,
Okay,
there's
that
no.
makes it very interesting. Yeah. Okay.
Yeah.
So there's like a big area of
Yeah,
active research.
yeah. Okay. Thanks.
So like Juliet Paluski, for example, I think is interested in this topic.
Yeah. So this potentially is an explanation for why we have the two different equilibria in our WTG models. Is essentially there are two states of the tropical atmosphere: dry subsidence caused by radiative cooling, and then moist convection in updrafts. So this, the WTG is potentially very important and useful tool for studying tropical convection, as well as a way of describing tropical meteorology and what happens. But now to what bottom-heavy convection actually is. Here are, bottom-heavy convection is primarily important because of the tropical energy balance. If you have, so this would be bottom-heavy vertical motion, where you have a maximum that's lower in the atmosphere, generally at the freezing level or the level of minimum moist static energy being the switch between top-heavy and bottom-heavy. So if you have bottom-heavy vertical motion, then you'll have divergence up here and convergence down here as the gradient or the curvature in the profile switches. And if you have bottom-heavy convection, that means you're going to be importing moist static energy that is much higher than the moist static energy that you're exporting due to this minimum. While as for top-heavy convection, you're going to tend to export energy because you're diverging rich moist static energy air and importing poor moist static energy air. And this leads to a state where bottom-heavy convection tends to be to destabilize a column and create more and lead to more convection and more precipitation, as it tends to also moisten the column, whereas the opposite is true of top-heavy vertical motion, where it tends to export energy and restabilize the column and remove moisture. But the question is, where do we see bottom-heavy vertical motion? And this is a plot of the ratio of the first principal or the second principal component of vertical motion over the first principal component. And this essentially gives you a normalized vertical motion geometry, where if you have the same ratio of O2 to O1, then you essentially have the same characteristics of vertical motion for that profile, so that when comparing any two, they basically will act the same. And when you decompose the data using principal component analysis like this, and then plot maps of the O2, O1, you can see that the East Pacific has a lot of bottom-heavy convection compared to specifically the West Pacific warm pool, which shows a lot of top-heavy vertical motion.
So it's not the amount of vertical motion that's related to the top heaviness ratio. It's
Yeah.
just set out, yeah. It's the shape of the vertical motion.
And this comes from any of several reanalysis data?
Yeah, if you do, I think this is with ERA-Interim or NCEP, but yeah, if you do NCEP reanalysis, ERA-5 or ERA-Interim, or even just smaller subsets of data, the vertical motion EOFs tend to look like those, and you can, plotting them out, the EOFs tend to, or the principal components also tend to map the same way depending on data sets. There's some change, but it's pretty
This
consistent.
signal is very robust.
And
The
it
signal
crosses,
showing there
it
is
crosses
very
La Nina,
robust.
El Nino boundaries, right, in the time series? So does it always look like this, or does it shift?
So this is the climatological, but depending on the state of ENSO, it can change.
Oh,
I
okay.
actually have,
Yeah, we don't need to look at that.
yeah, I have a plot I can show after the talk that basically depending on the phase, it does change this this setup. But yeah, this is the timing.
What does that mean when you have a region of bottom-heavy convection dominant, like in the East Pacific and the Atlantic? Does that mean that you just keep destabilizing the area, but you never release it?
Well, one consequence of it is the vertical components of the energy, or the vertical advection of the energy, tends to not be enough. So you either, in order to have a zero energy balance, you either have to have a different precipitation efficiency, or you can have a different amount of horizontal advection of energy. But yeah, it is basically the vertical advection tends to have a destabilized environment, so you have to have some other source
So
just in order to keep
in
it
those blue
secure.
areas, are you then exporting it to the areas that are red?
Yeah, if you look at maps or a zonal average of the advection, you can see in the West Pacific, the vertical advection tends to have a negative sign, whereas in the East Pacific that's reversed. So there is a tend for the energy to
That looks like the
move.
Walker circulation.
Yeah, and it is somewhat related, I would.
It's all upward vertical motion, though.
Yeah, so this is, yeah, been.
These are all regions with greater than average precipitation. So the Walker circulation has subsiding regions in it, right? So
Yeah, so these are all convective squares where there is mean convection. Yeah.
Maybe you already did this, but just following your argument, would it be true that if you did a linear regression for all those points and did the correlation for the magnitude of temperature gradient of the sea surface and and that pattern, then you'd get a high value of R squared, perhaps?
For
If the temperature gradient is a fundamental ingredient for explaining that, then maybe even one number at a snap, well, I guess it's a climatological plot. You can do a correlation coefficient spatially for those two variables, their temperature gradient magnitude and that ratio.
Yeah, I have a
Yeah.
simple model that makes
Yeah.
use of that idea.
Yeah, and I'll actually
Yeah.
talk a little bit more about that
Okay,
later.
sorry.
And that's a good question. That is basically what you would see. I don't know if anyone's done exactly that, but yeah. And in fact, the talk on Monday by Margaret Duffy will address similar things and in more depth. But yeah, when you have so yeah, we see bottom heavy vertical motion in the East Pacific. So, and it is important to the energy budget of the atmosphere. So now I'm going to move on to the two potential causes for bottom heavy vertical motion. The first one is that surface convergence is driven by sea surface temperature gradients, which essentially force the lower atmosphere vertical motion due to mass continuity, and this surface convergence then drives the vertical motion, and we don't see a lot of deep convection, which would lead to top heaviness there, because the low sea surface temperatures don't allow for deep convection.
Well, it is deep convection.
Yeah,
It's
the
not
convection
as
isn't top
deep.
heavy.
Top heavy.
Yeah, the better way to say it is, yeah, the convection isn't as top heavy because the sea surface temperatures are lower. The other idea is that bottom heavy convection is a consequence of the local thermodynamics causing the column to be more stable, and this increased stability leads to bottom heavy convection. Or an alternate is it's a combination of both of these because they are not mutually exclusive, and it can be both of them acting in concert, causing what we see with the bottom heavy vertical motion. First, I'm going to talk about the sea surface temperature gradients cause, and under this, if we have a sea surface temperature gradient like we see in the East Pacific from cold to warm, this imprints on the surface pressures, the surface pressure levels, which tends to bend them, creating this surface convergence. And because of mass continuity, we know that that leads to vertical motion. And then with this vertical motion, that's essentially convection, but we don't see it become top heavy because of the lower SSTs, like I said. One other part of this that's important is that this increases also the local winds, which also increases the amount of latent heating that you see due to evaporation, which could potentially be important to the system. But the primary importance and thing to remember is that generally the low-level winds lead to convergence. And like I said, we see these SST gradients primarily in the East Pacific along this cold tongue, where in the West Pacific warm pool, it's basically just a blob of hot water. In the East Pacific, we have very cold that approaches very warm, and this drives convergence and the meridional winds extremely strongly in that area along the surface. One way to see how this affects the system is if you have two modes of convection, a shallow mode and a deep mode. The shallow mode, you say, explains all of the surface convergence, which is caused by the SST gradients. And then you have a deep mode, which is determined essentially by the local SST and the local SST anomaly compared to the mean. Then you get, and from each one of these modes, you can ascribe a precipitation rate, and then they add linearly to give you the total precipitation. When you do this, you get a pattern of precipitation that pretty closely matches what's observed. So when we have The shallow mode can be well determined by essentially only what the surface or boundary layer is doing, and the orthogonal or nearly orthogonal deep mode is then determined by something else, and combining these gives you the total precipitation rate that matches well the observation. A much more detailed explanation of this is going to be given by Margaret Duffy on Monday, as she uses a similar model to explain the distribution of precipitation under global warming and climate change, and how the importance of the Laplacian of heating as opposed to just heating in general.
And this model makes a prediction for vertical motion profiles.
Yes.
Right, that's the relevance to this talk.
Seems like the Laplacian of the sea surface temperature matters here. So that if there's a second derivative of the sea surface temperature, then you get this bottom-heavy convergence. If there isn't one, but you have a large anomaly, then you get the deep. Is that a reasonable way to think about this?
Yeah.
Yeah.
Okay.
Yeah. That is essentially one complication.
That's the argument to
Mhm.
the model.
Yeah.
Oh,
That's,
okay.
Yeah, that is the basic model of, from back in Bretherton 09, and then the slight addition that Margaret Duffy added was to
Don't-
essentially.
don't-
Okay. Yeah.
don't.
But yeah,
We
that
gotta
is the
move
basics
forward.
from this model. So now on to the second explanation, which is essentially that the stability of the column is important to the bottom-heavy convection. Here on the left are temperature perturbations that were added to in SWTG simulations that are very similar to the ones we ran. The difference being those ones were two-dimensional and had constant wind and a different interactive radiation scheme. But when you add these temperature anomalies or perturbations, which tend to stabilize the atmosphere because we have cooling in the lower troposphere and then warming in the mid to upper troposphere. When you apply these to RCE simulations and run SWTG, you get increasingly bottom-heavy profiles. This idea primarily comes from observations from field campaigns like EPIC and PREDICT, where it was observed that a mid-level PV anomaly was important to cyclogenesis. So this mechanism, as described, is extremely important to tropical cyclogenesis, where we need to explain how we get from mid-level vorticity to surface vorticity in order to spin up the tropical cyclone. Normally, what we see in throughout the data in simulations is that we start with top-heavy profiles, which tend to have convergence at the mid-levels. This mid-level convergence brings together the vorticity in the area, creating a PV anomaly, and the temperature response of the PV anomaly is to warm the upper troposphere and cool the lower troposphere. When this is done, this tends to make the profile more bottom-heavy, which increases the surface convergence and actually spins up the tropical cyclone. And this is well supported by the data and the fact that we see a mid-level PV anomaly pretty much ubiquitously in tropical cyclogenesis, and it explains how we move from mid-level PV or mid-level vorticity to surface vorticity, despite having no explicit term in the vorticity budget. So the two potential causes are essentially a SST gradient-driven convergence, which is essentially a dynamical cause, and then a thermodynamic cause in which the stability of the environment leads to bottom heaviness. And so in this study, we use an SWTG model that was slightly modified from previous research on DYNAMO, and 3 separate MJO events done by Shugang Wang And the model itself is based off of WRF 3.5 and has interactive long and short wave, imposed horizontal moisture advection, and periodic boundary conditions. But the model used by Shuyang was time dependent because they wanted to simulate the series of events for the MJO, while we want to study the steady state. So in order to modify from his model, we take the mean of everything and use that as our forcing, as opposed to using the full variability profiles of moisture, temperature, wind, and moisture advection.
And we're parameterizing the large scale dynamics.
Yes. Yeah. So when we do test our model against their data in order to see if we can actually simulate the steady state or the mean conditions, we find that we actually do a pretty good job. So this shows in yellow is the simulated vertical velocity from the fully time-dependent model, whereas these, the green and purple, show our time mean or time-independent simulations. And as you can see, they fairly closely match the observations, which are here in red and blue. One important thing to note is that there's only one time-dependent line. That's because when you start the model in with the full variability at the start of the data, you enter into the dry equilibrium, and it can't recover from that. So they started it on October 10th. When we run the model using either start date of the 1st or the 10th, we don't enter into the moist equilibrium. So that seems like or that's an important aspect from that improvement, that we don't see the negative effects from the dry equilibrium. And we also get precipitations, which are not shown, precipitation rates that are much closer to the observations. For our data to actually input in the model, we're using data from two specific regions in the Central East Pacific and the West Pacific warm pool. And these regions were chosen because in reanalysis and GCMs, we see the canonical bottom-heavy vertical motion and top-heavy vertical motion that we want to study. And from each of these regions, we take a 10-year climatology of the temperature profiles, the winds, the moisture, the horizontal moisture advection, and the sea surface temperatures. We then plug those all into our model and allow it to run to equilibrium with imposed vertical motion. This essentially gives us a profile that is an analog to the real world, which allows us to then run WTG on it. If we were to just plug the data in directly into the model, then we wouldn't be able to adequately analyze the results, because there are differences between the simplified physics in the model and the full physics of the real world. So when we do this for both the East and West Pacific, we enter into the dry equilibrium. This could mean one of two things. First being our model isn't quite sufficient for exactly what we want to study, or the idea that we have is that it's more just saying that we're studying, or we're simulating the more common state of the atmosphere, which is dry subsidence. So without any sort of perturbations to the model, we enter into the dry equilibrium. In order to sort of study, break out of that and actually study convection, we have two different temperature perturbations, which are intended to study the effects of both stabilizing and destabilizing the environment. And these are the same temperature perturbations that were seen previously. And we also have several different moisture perturbations. The first being where we set the entire column to 85% relative humidity, and then two more which setting it to the column to 85% tends to dry out the lower atmosphere and moisten the upper atmosphere. So then we also have two different perturbations which isolate these effects, where one just dries the upper and the other or one just dries the lower atmosphere and the other moistens the upper atmosphere separately. So what we expect to happen from these two the two temperature perturbations are the stabilizing one we expect to lead to bottom heavy convection. The destabilizing one we expect to lead to more top heavy convection, as well as the more stable column we expect to produce more precipitation.
Do you also expect that to go back into the dry equilibrium?
No, we expect all of these, for the most temperature perturbations, I don't know of a one-to-one from the dry equilibrium to not, but it has been seen for the most part that applying these perturbations breaks you out of the dry equilibrium. But for that, we primarily were looking at the changing the moisture profile as being the important thing to change.
So to get rid of the dry equilibrium, we change the moisture, and we also do these experiments.
Yeah. And when we do them, we see here on the bottom the expected result from more simplified SWTG simulations. Or stabilizing leads to bottom heavy. When we do the same in ours, we do not see bottom heavy convection. In fact, we see essentially two different states, this extremely stratiform profile, and then the more deep convective flat profile. One important thing to note is that I don't have the moisture anomalies noted on here, so each of these three lines all have different moisture profiles to start with. And as you can see, the moisture doesn't really affect the normalized vertical velocity. Oh yeah, these are also, the vertical velocities have been normalized by precipitation amounts, because otherwise we would have very different magnitudes on the profiles and they'd be very difficult to actually look at. Yeah.
So for the unstable profile, it's actually a little bit more stable below 0.2, but that doesn't matter, I guess?
Sorry, can you say that again?
Well, for the finely dashed curve, that's the more unstable profile, but below 0.2 altitude,
Yeah.
it's more stable. And does that part not matter, I guess?
So
You have the temperature perturbation not touching the ground.
Mhm.
Maybe there's problems if you have it at the ground, so that there's uniform stability change with height.
Yeah, I'm not sure about that. That would be interesting to see. I believe because the surface temperature is so closely connected to the actual lower boundary condition, which we use as the SSTs, that I don't know how much that effect would be realistic. I'm not sure. Yeah, that'd be interesting.
I mean, the main point of this, right, is just that we're trying to demonstrate that our model can broadly capture what has been previously seen in the literature. Do you want to try to explain why that's the case?
Yeah. So the important thing is we don't see the canonical bottom-heavy convection that we were expecting to see like this, but we do see the same basic trend where comparing the stable to destable profiles, we see the stable and base profiles have this overall more deep convective look, whereas the unstable profiles tend to make this more stratiform profile, which means that the broad characteristics that we're seeing here are still in effect in our model, but they aren't leading to the bottom heavy convection that we expect. Yeah, Dan?
I guess I don't know how to interpret the top two plots.
Yeah,
So
the lines
you've
aren't
got two
clear.
different dashed lines there, which, so I see the destable versus stable, but for each one you have.
Yeah, so each of these are different moisture, initial moisture profiles.
Okay.
And for the most part, they don't make a difference, which is why I didn't
So there
note
seems to
them.
be some sort of history.
But you
Yeah.
have, you have the east and west Pacific plotted there, right? Or
Yeah, so this is the East Pacific
this is the
cases,
East.
this is the West Pacific cases, which I don't actually know the light blocks those. But yeah, so as you can see, the moisture from these, they're all grouped together. So the moisture profile doesn't tend to affect the shape of the vertical motion. It only changes the amplitude, except for 3 specific cases, which you can see
why don't you
here.
just point to 2 lines and explain what 2 lines
Yeah.
are? One's base, one's stable, one's more convective, one's more stratiform. Like, just
Yeah.
in terms of these lines, like, we only need to know about 2 of them, right?
Yeah.
And the rest are just variations. Can you just
Yeah,
point
exactly.
to 2 of them and make your point?
Yeah, so here we can see the destabilized profiles form the stratiform profile, whereas the stable here create a more deep convection where there's no
So why is there a dashed line that looks like there's a stable one that looks stratiform?
Because that one was one of the odd ones that was stratiform despite the moisture, or the moisture seems to be the thing that pulled it into the stratiform phase as opposed to being the temperature anomaly. Whereas broadly, the same mechanism, or moisture doesn't seem to affect the actual shape except for a few very specific cases, which I'm unsure why those specifically went one way or the other, but broadly, the temperature determines the shape, whereas the moisture determines amplitude. But yeah, like I was said, except for 1 specific case in the east and 2 specific cases in the west, broadly we have that the temperature effect is the more dramatic in altering the geometry of the profile. Moving on specifically to the West Pacific, like I was saying, the changing the moisture profile doesn't change the geometry of the profiles, which can be seen from the fact that outside of these 2 specifically, they don't actually, they all tend to clump on the same line when normalized by the precipitation, despite these stable cases and having around 20 millimeters per day, whereas these dashed stable lines have around 200 millimeters per day, so an order of magnitude different. And so, but we see the destabilizing profile tends to lead to stratiform conditions, whereas the other ones tend to lead to more convective profiles. We also see this in the East Pacific specifically, where stabilizing anomaly leads to the more deep, not necessarily deep, but not stratiform. We don't see any areas of descent. So comparing the stable to the unstable, there's a pretty dramatic shift in just the state of convection, and they look very different. Whereas changing the moisture anomalies doesn't seem to have this effect. But one very weird thing with these 3 lines specifically from the East Pacific is we get this weird periodic convection where the precipitation rate increases to a maximum and then begins to, after it reaches a maximum, the kind of convection changes from bottom heavy to stratiform and precipitation decreases. And this happens at about a 13-day period and depends on both temperature and moisture profiles. Because we see 2 of the cases are from the
And the boundary
the base.
conditions don't
Yeah.
have anything periodic in
Yeah,
it.
exactly, yeah. Everything is mean, everything is time independent, other than the interactive radiation. So these 3 lines all show the same sort of periodic. 2 have no temperature anomaly added, so they're just changing the moisture, the initial moisture of the column, and then 1 changes the temperature that the column is relaxing to. And we see this really weird periodic equilibrium,
Do you
which
think a tropical wave mode is being excited, or is that just a random aggregation timescale?
the timescale seems to be related to our relaxation time, but we don't currently have an explicit model of exactly what is leading to this this periodicity. But as you can see, it starts off with bottom-heavy vertical motion. Then, as the column moistens due to the bottom-heaviness, it reaches the precipitation increases until it reaches some break point where it transitions to this stratiform convection. And so, as it moves, we have increasingly bottom-heavy convection, and then eventually it switches to stratiform. Another way of saying this is we have a switch between congestus and stratiform convection, which we want to know two things specifically: what is transitioning from the congestus to stratiform and back again, and then what is making the specific cases do this periodic convection. You can look at this on the GMS phase plane, which, as a little refresher, you plot the convergence of dry static energy, which is essentially a measure of precipitation, and then convergence of moist static energy, which is how much energy you're importing and exporting into the column. And when this plots nicely onto a phase plane, which predicts whether or not you're going to see increased precipitation, and it also tends to move around the phase. So we have convection that tends to import moisture while increasing the amount of precipitation. Then it reaches a critical point given by the critical GMS, which is essentially just the diabatic terms over the the diabatic terms, and then it switches to decreasing, where energy is exporting and the amount of precipitation is decreasing. When we plot our simulation on the same thing, we only have vertical advection, but we still see the same motion around the phase plane. So the vertical motion that we have simulated seems to push us around the phase plane much the same way that we see it from the
Observations.
Yeah, from observations, which is exciting both for believing that this might be a real phenomenon that we can come up with a model for and apply to the real world, but also in believing that this phase portrait is describing the convective life cycle. Going forward, what we need to do is to figure out what makes this periodic, or to figure out what we need to do to the model in terms of modifications to actually observe the bottom-heavy convection that we expect to see, that we see in GCMs and reanalysis and in the data. To do this, we're going to more systematically explore the parameter space, especially the thermodynamic profiles that we are using in these models, as well as eventually getting to a place where we can include the convergence effects due to the SST gradients. We also need to look for a simple model that can describe these periodic convection, why only some of the simulations go to the periodic equilibrium, what controls that, and then what controls the transitions in the periodicity. And then also we need to explore the data that was gathered during the OTREC field campaign, which recently just concluded. The field campaign took place in, hard to see, but Costa Rica. We were there for 2 months flying 21 flights. Each of the flights would fly one of these 2 grid boxes, and every, I believe, 1 degree, we would drop a radio sonde, and from these we gather profiles of wind, temperature, and moisture, and then from the full gridded wind set, we can calculate convergence and divergence, and then from that, we can actually calculate the vertical velocities in situ, which is extremely important because there aren't really good observations of the vertical velocity profiles from the East Pacific and Western Caribbean. In addition to the flights that on the flights also, we had measurements of cloud ice, and also we had the hypercloud radar to observe the properties of the clouds themselves.
Of course,
Yeah.
what height were you dropping the sun from?
We around 42,000 feet, which is I think 14,000 meters. So generally above all of the convection, although sometimes not quite high enough. If you want an interesting story about that, you should ask Larissa for her harrowing flight. But we were also doing twice daily balloon sondes from 3 different sites, 2 in Colombia, 2 in Costa Rica, 1 in Colombia. And from that, we were able to actually measure bottom-heavy vertical motion. So here's the mean of the first 14 flights that we took. And as you can see, we do have a peak in vertical motion in the lower atmosphere. And if you break down each of the cases into the average mass flux between 5 and 16 kilometers, and then between 0 and 5 kilometers, which is essentially the break between bottom heavy and top heavy, most of the cases lie on this bottom heavy side. So that's extremely exciting that we actually took measurements. And with that, I'd like to thank Larissa for all the help in the research and for her immense patience in helping me out. I'd like to thank Vijit, my office mate, for all the support and help, and then also my committee, Mark Morgan, Dan, Stephanie, and Sam Steckman, and then everyone at AOS, parents, family, and friends. And with that, thank you all for your coming.
Back in the good old days, maps had latitude and longitude at the same scale, so that wind arrows had the correct orientation. When may maps get healthy again?
I'm not sure, but I don't know. Unless you have wind barbs specifically, I don't know if that's as important. And one of the complications is a lot of maps with those same scales tend to look pretty gross from other perspectives, and that the aspect ratio of the Earth, and specifically the tropics, is kind of warped, because you have 360 degrees on the coordinate and then only like 30 or to 60 on the ordinate. Yeah.
Don't just take a pill, do something serious about it.
In your periodic simulation, the boundary conditions are constant.
Yes.
Is there an interaction between what's happening? Because you have a small. My understanding is you have a small grid.
Yeah, it's 64 kilometers on each side, with 1 kilometer grid spacing.
Okay, and is that influencing that's not influencing the boundary conditions or your imposed large scale at all?
No, and in fact, when we move to a
There's no
larger
imposed
grid,
large scale.
we still see the same. We doubled the grid size and we saw the same periodicity, and I think it looked basically exactly the same outside of random model perturbations.
But there's no imposed large scale, right? The large scale is simulated.
Yes.
So I recently heard, and I don't know too much about this since it was something I recently looked into, that one of the big changes from ERA-Interim to ERA-5 is in the thermodynamics. So I heard that there were a lot of changes in thermodynamics in a that's one of the big differences between ERA-5 and ERA-Interim. So I'm curious as to if you were to try using ERA-5, how things would change or didn't change.
Yeah.
Just something that might be worth looking into.
Yeah, I'm not sure. That would be good to look into, and we're actually looking to use ERA-5 data going forward and essentially replicate what we did with ERA-Interim with that. But yeah, that would be interesting. That would to see what changes that leads to. But having looked at specifically the principal component analysis of the vertical motion between ERA-5 and ERA-Interim, they look very similar, so I'm not sure how deep those effects would translate. But yeah, that would be interesting to look at. Yeah.
You said that, so you parameterize, it's a weak temperature gradient, so parameterizing that is just a Newtonian relaxation.
Mhm.
But then you said that for your model, you added horizontal moisture advection. That was the large scale moisture advection?
Yeah. There's essentially that was the choice. There's 3 normal ways of handling moisture in the WTG simulations. One is to impose the moisture advection, which was done in the DYNAMO simulations that I showed from Shuang Wang. Another way to do it is to relax the moisture to the environmental profile as we do with the temperature, and that's more what Adam Sobel started with. And then there's another where you can just entrain moist air from the environmental profile. We chose to do the imposed moisture advection first to stay consistent with the previous model studies, but also because the imposed moisture is, or the moisture advection is hard to get correct. So as a first start, we'll just take what we see from the simulation and just use that as a good first step.
So that there isn't then kind of this constant flux of moisture.
Mm-hmm.
It's dry air, yeah, it's dry.
And if you've got these 2 modes, one that precipitates more than another, you could shut down precipitation, advect moisture in, and trigger it again. And it seems like
The
that,
horizontal moisture.
that horizontal moisture advection could
Yeah.
be a key to your periodicity.
Yeah, exactly, and that's one
It's
thing we're going
constant
to
in time.
investigate.
You should
Yeah,
put
it
down
is.
it's constant
So
in
yeah,
time.
the advection itself is constant in time, but yeah, as a
But it's a flux,
just
right?
imposed, yeah, just as an
And you got
imposed forcing.
a very low sink of moisture in your atmosphere,
Mhm.
depending
Yeah.
on which mode you're in.
But the question I have is why we don't see that same effect. One, in all the simulations, I would, I guess, naively assume that
Right.
sort of model setup would be a more systematic thing, and we wouldn't see it with these very specific temperature and moisture profiles. But also then why, because the surface fluxes also tend to be just a constant, infinite source of energy into the column. So why we don't see the same sort of flip-flop just from that forcing. But yeah, that is definitely a thing we're looking into. Yeah, John.
A lot of intriguing things here. To just comment on that last one, to the extent that I think I might understand it, I might be way off. Different temperature and moisture profiles will give you different theta E profiles in the vertical. That
Yes.
matters, right?
Mhm.
For some of this exact thing that Brad's talking about. So that's one thing. But I was intrigued by the tropical cyclogenesis connection, and you had a slide where you go from top heavy to spinning up some PV disk in the middle troposphere, and then you
Yeah.
go to the bottom heavy. That is not a pathway that goes either way. This is definitely directional, right?
Mhm.
In the theory.
Yeah.
What I'm a little confused about is how does the top-heavy convection generate a PV anomaly in the mid-troposphere? Is it just by convergence, or is it by column stretching?
No, and
combination.
It's almost entirely due to the convergence of the environmental vorticity by the fact that we have the top-heavy profile. If you were to look at a large enough circulation, ring of circulation around like a mesoscale complex, then both the tilting and the twist, or so the stretching and the tilting terms both tend to cancel out and don't actually affect the vertical vorticity in that way. So you need the convergence in order to actually spin up any of the cyclones.
And then how does a PV anomaly, say straddling the equator, come up with that thermal structure? Because that, as far as I understand it, that's a function of something like gradient or thermal wind balance, which of course won't apply
If
to
you
the
have-
degree. So that's what I'm kind of wondering about too.
Yeah, if you have a balanced wind, so if you look at the time scales that are big enough or long enough to that you can have a balanced wind, a balanced thermal structure in the winds, then you can have PV anomalies.
Okay, then it'll have that structure
Yeah.
thermally, I understand.
But
that.
yeah, you
Okay.
have to, in the tropics, you have to be a lot more careful that you're actually looking at a balanced flow, because there are the unbalanced parts that can exist.
Okay.
on
And
top.
then if I could add one more question. You can't go, your first slide showed where you have no temperature gradient at all at 600 millibars in the tropics, and then suddenly you have a strong one, that's where all the jet structure is. How far from the edge of the beginning of the baroclinicity in the mid-latitudes or subtropics do you have to be to use the weak temperature gradient assumption? You can't be right on the edge, right? You got to be somewhere right near the equator?
Yeah, it's sort of near the equator. I think I don't know if any specific research has been done to sort of look at those, but I know I think around 10 degrees, which is where you start to see the hurricane spin up, I think
Yeah.
would be a sort of middle point where you still have a weak enough temperature gradient or a weak enough Coriolis parameter that you can still assume weak temperature gradients, but then you still obviously have enough vorticity to have tropical cyclones.
Okay, thanks.
Yeah.
That nice move you have, going through the hysteresis clockwise, what do you make of that asymmetry that it can ramp up quickly, but then that it kind of there's a hitch coming back down in maybe 4 out of 6?
Yeah, so where it like essentially pauses in this region.
Yeah.
Yeah, that's probably something to do with the fact that the diabatic terms tend to slow the system down. In our observations, there's a switch in the radiation that happens as it changes phase that I think helps to sort of, or that impedes the progress and sort of stalls it around those equilibria points. But that's more related to the work, or more a conclusion coming from the work Vidit did, or is doing on the phase portrait analysis. And essentially what happens is, as you reach that point, the energy is more going into switching the phase than to actually propagating the system. So you have two essentially saddle points in the cycle. Yeah. There are no other questions?